Tim started off his career in X-ray imaging back in what was the USSR at the time at the University of Leningrad. He remained there for another 2 years working at the Institute of Microelectronics Technology and then moved to Australia in 1993 to take up a position at CSIRO just across the road. He's been working there ever since and is now a senior principal research scientist as well as an adjunct professor at the University of New England. Tim has been called a grandmaster of X-ray theory by David Paganin, who's quite an authority on the subject, as you all know.
Thank you.
And he's done some excellent work, mainly in X-ray phase contrast imaging and also tomography, looking at phase retrieval algorithms, which have been implemented in this software extract, which is widely used. And also looking at theoretical optimization of the imaging setup and the analysis. Today he's going to talk to us on contrast, spatial resolution and signal to noise in inline X-ray phase contrast imaging. Welcome.
All right. Okay, thank you very much. I hope everybody can hear me. If not, I'll use the microphone, but just let me know. Just a few brief remarks before I start. So first of all, thank you very much for this opportunity to present my talk here. Secondly, I was asked to include some introductory slides at the beginning, so I apologize for the triviality of those things, but that's how it is. I also included quite a bit of material which I presented previously, including here at Monash maybe a year ago, but I put it into the new context, so hopefully it will not be very boring. And another thing which I really need to apologize for is that I actually this time I included quite a bit of mathematics because I thought that some people may be able to enjoy the, in some cases, what I think are reasonably beautiful formulas that we have been able to derive in some cases. And if that mathematics actually looks impenetrable or not as interesting as I feel about it, just ignore it. I'll just, in every case, try to give the overall message, and that should be enough. And the last thing is that the results I'm presenting here today are by no means my own results or just my results. They are contributions by many people. And I have a slide at the end which have a list, although maybe incomplete, of the people whose results will be presented. Okay, so this is the first of the trivial slides, which shows the general, very simple layout of the X-ray, so-called inline or propagation-based imaging, with the X-ray source on the left, X-ray detector on the right, and the sample in the middle, various coordinates, and the two very important geometrical parameters are the distance R1 between the source and the object, and the R2, the distance between the object and the detector. What else? In the business of X-ray imaging, the image is typically, the image characteristics are determined, apart from those geometrical parameters, and of course the source properties, they are determined by the properties of the sample, which is usually described in terms of its complex refractive index. The real part delta, which is responsible for refraction of X-rays, and the imaginary part beta, which is responsible for X-ray absorption in the sample. So those quantities will be appearing time and again in this talk. The other thing which I wanted to mention is this: in the range of X-ray energies that I'll be discussing, the delta is usually of the order of 10 to minus 5, 10 to minus 7. Beta is much smaller. So the gamma, another quantity which I'll be using all the time, is the ratio of delta to beta, is usually of the order of thousandths in that X-ray range. And for the type of samples that I'll be considering, mostly light chemical elements present in this type of samples. So another of the trivial slides, the way the absorption and phase contrast is formed in X-ray inline imaging. Of course, the absorption contrast appears due to differential absorption of X-rays as they propagate through the sample. And the phase contrast occurs because of the refraction of X-rays. And then on transmission, that leads to interference and to some specific contrast, which is schematically shown here. So we usually have so-called Fresnel fringes at the edges and interfaces of the sample. Oh, sorry, at the edges and interfaces of the image of the, sorry. I probably don't have to clarify it, but I'll still try. So the fringes appear near the images of the edges and interfaces of the object. Another important thing to take into consideration in this context is that delta and beta and correspondingly absorption and phase shift have very different dependence on the X-ray wavelengths or energy. For example, at 50 angstrom, the thickness of the carbon sample, which leads to the 1/E attenuation and to 2 pi phase shift in the sample, is about the same. The same layer of carbon induces similar effects. Well, if you go to much shorter X-rays, like for example, 1/4 of angstrom, the hard X-rays, then in order to achieve the 1/E attenuation, you need 435 millimeters of carbon, while for 2 pi phase thickness, you only need 132 microns. So phase effects, in a way, become dominant for hard X-rays compared to soft X-rays. This picture is supposed to demonstrate that in inline or propagation-based, I'll be using these terms interchangeably, inline or propagation-based X-ray imaging, the propagation of X-rays can improve the quality of the image in a sense that the contrast and spatial resolution can increase compared to the contact image. So if you increase R2, roughly speaking, then the image may become better. And if we magnify that image, it becomes even more obvious. So you get a much improved visibility of soft tissue details in the propagation image compared to the contact image. And what I want to do in this talk is to try and quantify this improvement in various ways and also discuss the ways in which the imaging system can be optimized in order to maximize these improvements. Okay. So speaking of quantification, as I already said, the image properties are determined as far as the sample is concerned by the complex refractive index. So in the so-called forward problem, where we go from object to image, we go from the three-dimensional distribution of the refractive index to typically two-dimensional image. Or if we are doing a tomographic experiment, then of course there will be a third parameter corresponding to the rotation angle of the sample. In the inverse problem, we go in the opposite direction. So we go from image or images, which may depend not only on the coordinates in the image plane, but also on some additional parameters. We are trying usually to retrieve in some way something resembling the distribution of the complex refractive index in the sample. And under the so-called projection approximation, the image properties or distribution of image intensity is a function of the two values, which are here denoted as mu naught and phi naught, which are correspondingly the linear integrals through the sample along the trajectory of X-rays, integrals of the imaginary and real part of the refractive index. So in order to go from an image to the object, we first want to retrieve the distribution of mu naught and phi naught from the measured distribution of image intensity. And this is the so-called phase and amplitude retrieval problem. In a general formulation, the problem can be stated, the phase retrieval problem can be stated as the reconstruction of the phase distribution and intensity distribution in the image plane from the measured, and intensity distribution in the object plane from the measured image plane intensities, which collected at one or more image planes, so that typically at different distances between, say, the sample and the detector. Well, because we are dealing with the method where we have no optical elements between the sample and the detector, everything is determined by free space propagation. So this is the usual Fresnel integral equation for the image intensity. And in this general form, we need to solve this nonlinear equation for phi naught and possibly for I naught from the known right-hand sides, which again, as I previously said, can be collected for different values of the distances between the, say, detector and the sample, and maybe different energies and the different rotational position of this sample. So there are different schemes, some of which I'll probably mention later in the talk. But this is, in a sense, the most generic formulation of the problem. Now, two special cases where we have special types of objects. The first one is the so-called pure phase object, which it's the object which has negligible absorption of X-rays at given energy. And the second case is where so-called homogeneous objects, where the phase and intensity are related through a constant which doesn't depend on the position in the image. And that constant is, of course, equal to delta to beta. So this is the type of objects that I think David Paganin was the first to consider. And since then, people call it by different names, but usually homogeneous or monomorphous, sometimes objects. And the subclass of these objects are objects consisting of a single material, but possibly with different density in different parts. So in order to solve that general nonlinear equation for the phase, we typically linearize it under certain assumptions. And the first assumption is that the distance between, well, I have to be imprecise at this stage, but let's say the distance between the sample and the detector is short enough, so we are in this so-called near field. It can be described by saying that the Fresnel number, which I'll define later, Fresnel number has to be large. Under this condition, the equation can be linearized, and what we get is the so-called transport of intensity equation, where I think I have defined already all the values, so I don't have to do it again. Just to mention that for the two special cases that I just listed, we have simplified forms of that equation. For the homogeneous objects, we just substitute this relationship between phase and intensity into the TIE. TIE is short for transport of intensity equation, of course. And we get this equation for the homogeneous objects. In the case of pure phase objects, we get this equation where the intensity I0 is constant because we assume that the incident intensity is uniform and the object is non-absorbing. By the way, one thing I forgot to mention at the start of the talk, that if there's something unclear in what I'm saying, or if I'm saying something stupid and you want to correct me, please do. But if you have more in-depth questions, I would prefer to answer at the end of the talk. But please interrupt if I say something wrong, which is quite possible. Another form of the linearization of the general nonlinear phase problem can be achieved by assuming the so-called weak object. This is equivalent to the first-born approximation. And in this case, which, by the way, as far as I started to mention people, Andrew Pogany contributed in this area quite a lot. In this case, it is more convenient to work in the Fourier space rather than in the coordinate space. So this hat on top of various symbols denote Fourier transform. And correspondingly, these psi and eta are the coordinates dual to x and y. But I won't be using this equation much, so I just want you to look at it in a sort of a bird's eye view and just appreciate that the whole thing linearizes with respect to psi naught, which is in this case the quantity which is related to delta and beta, depending on whether we consider the real or the imaginary part of psi naught. So anyway, two cases of the linearization of the phase problem, which I wanted to mention at this stage. Now I'm going back to this general scheme of things and would like to define a few further quantities which will be used in the subsequent results. Magnification, of course, is defined as usual as the ratio of the full distance between the source and the detector to the distance between the detector and the sample. The so-called defocus, or I don't know, defocus distance, or there are other terms probably for this value R prime, but it's a reduced propagation distance, which is, I think, well familiar again to most people in the audience, so I won't dwell on it. Another quantity is the sigma, or if you like, the variance of the imaging system, which is a function of the, well, it's basically something which is closely related to the width of the point spread function, which can be expressed through the width of the source distribution and the width of the PSF of the detector in this form. And the dependence on the magnification is very important for subsequent purposes. So just have a look, and I'll be reusing this equation a lot. And finally, the main hero of this talk is the Fresnel number. You can see it's defined here in this form through this width of the point spread function in the numerator. And in the denominator, we, of course, have the usual product of the reduced propagation distance and the wavelengths. I'll be using different forms of Fresnel number during the talk just to make things more complicated. But they all will look very similar. This is the simplest model of the sample that we use to derive analytical expressions for the key imaging parameters, such as contrast and spatial resolution. The model is the blurred pure phase edge. So we have an edge with materials here sitting on the right, empty space on the left, X-ray is going in this direction, perpendicular to the edge. And this is the profile of the edge, including the blurring, which is described by its own parameter sigma. It will be sigma object in the subsequent formulas. So the mathematical description for the phase profile after X-ray planar wavefront propagates through that edge, the mathematical description is simple. It's the Heaviside function or the step function convolved with the, if you like, point spread function of the object, which really the blurring of the edge, and multiplied by the maximum phase shift, which is determined, of course, by the refractive index and the thickness of the edge. So this is the model, and you'll see, depending on various parameters, primarily on the Fresnel number, typically in the propagation images, we'll have these Fresnel fringes of various amplitude and width, depending, as I said again, on the Fresnel number, if that Fresnel number is properly defined. So, okay, details to follow, but I think the next slide will be the scariest. Yeah, it is. So again, apologize for the mathematics. The take-home message is very simple. Given that model that I just presented on the previous slide, we can derive an analytical expression for the image intensity in the vicinity of the edge, right? In very simple terms, which then allows us to derive analytical expressions for the contrast, signal to noise, etc., etc. And the expression is so trivial only in the near field. In the far field, it's a bit more complicated, so I won't give it here. But I just couldn't resist to, maybe in this case, to show how it's derived, because I think it's reasonably elegant, if I can use the word.
What's the functional form of the point spread of P object in this expression?
I think in this case it's a Gaussian. So I think in this context we assume that all the point spread functions are Gaussians. So when you convolve them, the variances are added. So this is the transport of intensity equation, and to add further to the confusion, I wrote it in terms of the so-called spectral density rather than intensity, which is in principle, again, even if somebody don't know what it is, it's a trivial thing. It's basically a monochromatic component of the intensity in the case of polychromatic radiation. So just you can look at that and consider it being an intensity as well for the fixed wavelengths. Nu is trivially related, is the frequency which is related to wavelengths y the speed of light. So again, this is the transport of intensity equation for the spectral density, including magnification as a factor. And on the right, we also have the blurring introduced by the system, which consists the blurring due to the detector and the object. If we substitute the phase function for the blurred edge, which is, again, contains this Heaviside function and the Gaussian function for the blurring. And so here we need to take the second derivative. So we take one derivative to the Heaviside function, get delta function, take another derivative and move it to the right of the convolution operation and differentiate the convolution of the two Gaussians, which of course give us another Gaussian. And this is the form, the delta function, of course, convolved with anything else is just a value of that function in the point equal to 0. So what we get is the first derivative of the Gaussian, which I think you can readily recognize has this form, which we know well from the Fresnel integral evaluation in the general case. So that indicates that this analytical formula indeed reflects quite well the usual behavior of the Fresnel fringes. But on the other hand, because it's analytical, we now can estimate everything, the height, the widths, of that function and therefore calculate things like contrast or spatial resolution. I won't go into further details, and by the way, I just presented the analytical case for the near field region. For the far field, it's more complicated, but what we get in the end for the spatial resolution is that simple curve, which near field region is here on the left, because it's all in terms of the inverse Fresnel number, which I wrote here for reference. So small inverse Fresnel numbers correspond to large Fresnel numbers, of course, or for small propagation distances, R prime. So this is the near field, therefore. And here, the spatial resolution is constant if you divide it by the width of the system point spread function. So the spatial resolution here is just the width of the point spread function. And here, the asymptotic behavior is like square root of the product of R prime and lambda, which one could readily recognize the width of the first Fresnel zone. So the spatial resolution here is the maximum of the two values, the width of the point spread function of the imaging system and the first Fresnel zone. I think it's reasonably simple result. The next one is the contrast in the same coordinates. If we divide it by the maximum phase shift, which is a constant in this context, we get again a simple curve with the minimum, which can be described as the minimum of two quantities. The first one is a constant multiplied by the inverse Fresnel number, so it's a straight line in this area. And the second quantity, which is actually the asymptote in the far Fresnel region, the second quantity is just a constant. So if I just swap between these two slides quickly enough, you can probably see easily that the two curves have a complementary behavior, which I will discuss later. And just maybe one sentence now is then obviously there is a trade-off. One can either improve the contrast or the spatial resolution by going along this axis, but not both. Just a word about the signal-to-noise ratio, which is defined here in terms of the integral signal, where integration is over the area equal to the first Fresnel fringe along the edge. Sorry, it's probably have to go to this picture. So one dimension of that area is this one, the area under the first Fresnel fringe, and the second dimension is orthogonal to that because the sample is, of course, or projection of the sample is two-dimensional. But this second dimension is basically arbitrary at this stage, arbitrary length Ly. So integrating the difference between the propagated and incident intensity over that area, we get the signal, which is due to the phase contrast. And we define noise as the square root of the what we call sometime, or I call, an incident dose, which is the product again of that area and the incident intensity or the spectral density, if you like. Okay, so signal to noise is that signal related to this noise. And using this definition, it's possible to show that it can be approximated very simply as the product of a constant times the contrast times the square root of the dose. So the take-home message is that the signal to noise basically behaves like contrast under these approximations. We verified these analytical formulas for contrast and spatial resolution using numerical tests evaluating the full Fresnel integrals. This gave us what called here exact numbers for the contrast and the spatial resolution. Then we used our formula which describes the behavior both in the near field and in the far field. You can see that the agreement between our approximate formula and the numerical evaluation of the Fresnel integral, the agreement is very well, both for the spatial, very good, both for the spatial resolution and contrast. And finally, we compared these numbers with the results obtained by the TIE approximation and the far field approximation, which is basically those two curves which I showed you. Okay? And as you can see, if you go across the curves, it's the blue area. The approximation, again, is quite reasonable, both for spatial resolution and contrast. So this is the far field, this is the near field, and correspondingly the contrast is constant in the far field, the spatial resolution is constant in the near field, but again, the agreement with the exact numbers is very good. And then Andrew Stevenson did a number of very nice and accurate experiments using our laboratory microfocus X-ray source and the imaging plates. And we got also quite good agreement between the contrast and resolution which we obtained from the images of these phantom, which consisted of the two plastic sheets crossed. So we were evaluating the Fresnel contrast at the edges and the spatial resolution in terms of the width of those fringes under different imaging conditions. The agreement between the experimental numbers and our analytical expressions was again quite good. So we understood that we can believe these formulas and use them for things, for example, like optimization of the imaging system. And one way to optimize it, one sort of a practically meaningful way, is to try and maximize the signal to noise in the image while keeping the incident intensity constant. That's one way to do it. The other way to keep, for example, the dose constant. It depends on what one wants to achieve. But anyway, under the assumption of the constant incident intensity, it turns out that the signal to noise has this formula which depends quite trivially on most parameters. For example, it says that if you increase the overall length of the system, you can get a better signal to noise. We know that. If you decrease the size of the source, the resolution of the detector decreases in terms of improve, and you make the object edge sharper, you'll get larger signal to noise, of course. So the only non-trivial dependence is on the magnification. And at both ends, at magnification equal to 1 and magnification equal to infinity, the signal to noise is actually 0. So at the two limits, it's 0. So somewhere in between, there is maximum. And it can be calculated. The interesting thing is that for the case where the source size is equal to the detector resolution, the optimum magnification is equal to 2. This is a recurring result, a well-known result. But it's nice that we got the same result as everybody else. In this case, it gives us more trust into the other results which can be derived from this formula. Now, this was all old results, but when I was preparing the talk, a strange idea came to my mind, is that we have been talking about this trade-off between spatial contrast and resolution all the time, but in principle, people wouldn't mind to have an optical system, an imaging system, which optimizes both to some extent, because one typically wants to have both good contrast and good spatial resolution. So I thought, well, what if I try and combine these formulas in such a way that would hopefully give me the recipe for the optimal system, which gives me the best of the two worlds, right? And that has some probably remote parallels with the uncertainty principle, because again, you cannot improve the spatial resolution and the detection of the impulse simultaneously. But I guess what you can try is to minimize the phase volume, the product of the two. And that's essentially what I'm doing here. So I'm using the expression for the spatial resolution and signal to noise, which I showed you before, for two different expressions for the far field and the near field. And I divide one by another so that the product is this phase volume. And if I maximize the product, I maximize SNR or minimize the resolution, which is what I want. So the expression which I get in this case is actually this thing, again, different for the far field and near field. But what's easily detectable is that here the maximum is achieved when the Fresnel number is the largest, right? And because this is only valid for small Fresnel numbers, so the maximum is achieved when Fresnel number is 1. Here, the maximum is achieved when the Fresnel number is the smallest, but the formula is true only for Fresnel numbers larger than 1. So again, the maximum is achieved at the Fresnel number equal to 1 point. So we get this curve with a single, sorry, in this case it's inverted, a curve with a single maximum at the point where Fresnel number is equal to 1, which is nice. And we have the upper limit, which is this very simple expression, again. And in terms, if I substitute the expression for the dose, it's more convenient than to just square everything. Then we get an even more trivial expression that this quantity, the phase volume, it cannot exceed the square of the maximum phase shift times the incident intensity. Of course, the more intensity, the better result. The size of the feature in the orthogonal direction. So the more times we can reproduce the effect and average it, of course, we'll get better result. And the width of the system point spread function. Again, obvious thing. Just in parallel, people often consider so-called figure of merit in this business, which is the, oh God, I'm badly out of time, sorry. I'll have to rush something, but I want to make this point quite clear because this is something new. The figure of merit is the signal to noise ratio divided by the square root of the dose. So the good thing about it that it doesn't depend on the dose, so you can optimize the imaging system at a fixed dose, which is important in things like medical imaging, right? And so in parallel with that, I introduced form ++, which is a better form, supposedly. And I divide form by the spatial resolution, and that has an even simpler expression. It just the maximum for that thing is basically the maximum phase shift divided by the width of the point spread function. Well, let's take it just one step further and combine all these formulas, and we'll see that again the only non-trivial dependence of all these formulas is on the magnification. So in order to maximize all these forms or magical ratios, we need to minimize the width of the system point spread function. And if we just differentiate it and equate the first derivative to 0, we get this expression, which can be viewed as the recipe for the optimal magnification. The optimal magnification has this form. So it's 1 plus the ratio of detector. Well, I won't be reading it, it's obvious. So just a special case for this source size equal to the detector resolution. Again, optimum magnification here is again 2, which is good. But here we get new, I think, and almost trivial formulas for the optimum distance between the detector, the source and the sample, R1, and the sample and the detector, just simply in terms of the source size and the detector resolution, and the two things are independent. So one can easily optimize the system, and just give two quick examples of that. In one case where it corresponds to something resembling our in-house X-ray imaging system with the small source size and moderate detector resolution, which probably I kind of artificially improved, but anyway. So from this we get the parameters like source to sample optimum distance 25 centimeters, detector to sample 1 meter, which is in agreement with what people usually observe. And another example is the synchrotron beamline. In this case, the source vertical source size is 16 microns, and the horizontal is 320, which gives us two different values, optimal values for the source to object distance, one being 16 meters and another 6.5 kilometers. The actual length of the beamline of 140 meters is somewhere in between, which is again not unreasonable. Okay, looks like I may be skipping a lot, which I'll do, I think. There's an independent part after that, so I'll just won't present it. It's all right. Yes, I'll probably may even stop at this point. I'm supposed to finish, sorry, at what time? 1:50? Sorry? 1:50, 1:55. Okay, well, a couple more slides then. And in that case, I actually want to jump all the way to the end, or almost to the end, because here are some other new results. New results, it's another way to look at the inline imaging, phase contrast, and how it can improve things like signal to noise, for example. People who work in this area know very well that phase retrieval, which I described, tends to increase visibly signal to noise in the images. But I don't think anybody tried to quantify that effect yet. And this is something which largely my colleague Yakov Nesterets has done in recent weeks and months. And this is his results, which I want to present here. So phase retrieval can be viewed as the backpropagation of the image from the image plane to the object plane, right? Because this is the phase retrieval in terms of TIE. This is the image. You apply phase retrieval formula for homogeneous objects, and you get the image distribution in the object plane, intensity distribution in the object plane. But what effect this operation has on the signal to noise? Using some reasonably heavy mathematics, Yakov has proven that it gives us a gain factor which can be analytically described, a gain factor which is defined in terms of the reduction of noise in the phase retrieved image compared to the image which is collected under the same condition with no propagation distance. I hope it's clear enough. So we are comparing contact image with the image obtained by phase retrieval in the same plane. Okay? And compare the noise levels given all the other parameters are the same, of course. So that gain factor can be expressed as the ratio or the square root of the ratio of gamma, which is the delta to beta, to the minimum Fresnel number, which is just a Fresnel number defined in terms of the detector pixel size. Right? This is a new result, and I won't go into the details because I don't have time, but the maximum gain factor which can be achieved turns out to be approximately 0.3 times delta to beta. So if you do the phase retrieval in this context, then you can achieve sometimes a very significant gain in signal to noise, it can be, if you can look at this graph, I'm sorry for the numbers being small, but you can get the values in thousands, right? And of course, delta to beta, typically as I described at the start, under typical conditions, delta to beta is of the order of thousands. So this is the maximum gain factor, something new. And the same or similar result has been derived in the case of the tomographic imaging. So when one does this phase retrieval and then conventional tomographic reconstruction and looks again at the gain of the signal to noise after that procedure compared to conventional tomography where contact images are used with no propagation. Here the gain factor is even larger. It's proportional. This second factor is more or less inconsequential, if I can say that. Apologies, Yakov. But the first factor is very similar to what you've just seen for the planar imaging. Only here there's no factor of no square root, so it's a square of the previous factor. The maximum gain is proportional just to the ratio of that gamma to the minimum Fresnel number. Okay, and we managed to compare these formulas with some experimental data collected recently. The data was collected with some simple phantom at the CIRMAP beamline of the electron synchrotron. Materials listed here were present in the sample, so different delta to betas, quite a range. So we had something to compare. And we did CT reconstruction without and with phase retrieval. You can, of course, immediately see the visible improvement noise here, but we actually quantified that and compared it with the numbers coming from the theoretical formulas. So you can look at the two, see that the agreement is pretty good. And we used two different values of gamma for the phase retrieval. And in both cases, there are some exceptions. For some reason, the material which we thought we know the best, water, gave us the worst agreement. But for everything else, the agreement is pretty good. So we got some confidence that this formula may be describing quite correctly what one have been observing in terms of the improving image quality as a consequence of phase retrieval. And of course, we were not first just to notice that. There were, of course, very good papers by David and other people from this department where this fact was mentioned many times. So what I think new here is that we now have the analytical expression, which at least under the specified condition defines this gain in the image quality and also sets the limit to which the quality can be improved. And I stop at this point, and this is the, as I said, an incomplete list of people whose results I have been using in this talk. Thank you.